In this section, we're going to look at several types of problems and hopefully inspire you in your thinking and how you try to solve them. So we have about 7 examples here. I'm picking them out of the book, but the textbook generally does their solutions differently than I'm doing here. So you might want to keep that in mind. If you don't like the way I do something, maybe take a look at your book. Or if you're reading your book and you don't like what they're doing, maybe you'll like what I'm doing. So let's start with this one. Here we have tickets for a fundraising event were priced at $10 for children and $20 for adults. Shauna worked the first shift at the box office, selling a total of $130 worth of tickets. However, she did not keep careful count of how many tickets she sold for children and how many for adults. How many of each ticket type, child and adult, did she sell? So let's take a look here. I think what I did is I created myself a table. So let me start with that. And we start looking at the number of possible adults and children that we can have. For example, let's start simple with the child. If we have one child, they spent $10 on that one child. That means that there is $120 left. So with one child, that means we have $120 left. Well, if we take that and divide it by 20, we get our 6 adults. So one child and 6 adults. That is an answer. That's not the only answer. So one of the problem-solving hints that they're trying to throw at you here is that some problems could have more than one answer. And depending on the situation, you may want to evaluate the different answers to see if they seem reasonable. Now, honestly, to see one child and 6 adults at a theater would seem strange. Now, it could happen that a parent takes their child to the movie and maybe the other 5 were just random adults. It's an unusual combination, it seems to me, but nonetheless. Let's go with 2 children, and I'll just keep doing this till I exhaust all the possibilities. So with 2 children, that's $20 that has been spent. That leaves $110 left over. And if we divide that by 20, we get 5.5, which is not really possible. So this situation here, we can't have. We move up to 3 children. So now the children have spent $30. That leaves $100 left over for the adults. If I divide the 100 by 20, I do get a number now. I get 5. So remember, I'm going to cancel this one out. Let me try 4 kids. So that's $40. That would leave $90 for the adults. And if I try to divide that 90 by 20, I get 4.5. Obviously, that's not a solution, so I'm going to cross that out. Now, what I'm seeing here, though, is a pattern. It looks to me like only the times when you have an odd number of children will you have a solution. So when I get to 6, that won't have an answer, for example. But if I have 5 children, they spent $50, that leaves $80 for the adults. If I divide those $80 by 20, I get 4 adults. Not only do I see a pattern here, I don't have to do any more computation, because as the odds go 1, 3, 5, and then 7, the adults are going down 1 unit. So here we'll have 3 adults. And then that's all I got to do from now on. 9, 2, 10, sorry, I made a mistake, 11, and 1. So we have a total of 1, 2, 3, 4, 5, 6 possibilities. These last 2 seem reasonable to me because you could have an adult taking a bunch of kids to the movie, maybe for a kid's birthday party or something like that. So these have a variety of reasons or not reasons. But when you have a situation like this, if the type of solution matters, then you have to evaluate all the answers and see which one you like best. Here, we just cataloged all of the answers. In this example, we have Jack and Jill are running a 100-meter race. Jill wins the race by 5 meters, and that is, she ran 100 meters while Jack only ran 95 meters. Well, apparently what they want to do is they want to make sure that they cross the finish line at exactly the same time. Or, well, actually, let's see here. If they decide to run again, but this time Jill starts 5 meters behind, who's going to win this race? So first, let me draw a picture. I found the picture very useful here in my thinking. So let's have them start here. So there's Jack, there's Jill, and we'll have them end over here somewhere. Only Jill goes the whole 100 meters. So let me write hers down, 100 meters. Jack comes up short. Let's say about to there. So he's got 5 meters that he didn't account for. So what they're going to do now is they're going to move Jack back, Jill back 5 meters. So the new look will be like this. So Jill will start back here. And Jack will start on the start. All right, now here's the end. So Jack is starting here. All right, I'm going to stop him at 95 again. We know that Jill, in the same time that Jack could run that 95 meters, Jill could run 100 meters. Well, there's 5 meters for Jill. There's only 95 to catch up to Jack. But now they're even, right? She's caught up to him. The thing is, though, Jill's a little bit faster than Jack. So the fact is, from here on out, Jill's going to be a little bit faster, and Jill is still going to win the race. So Jill's idea to put herself back 5 meters didn't work. Maybe put herself back 6 meters, or a way that you can get this to work, so it'll be perfectly even, is my proposed solution is this. Let's have Jack here and Jill here. I'm going to have Jack start 5 meters earlier than Jill. So then let me get it to the end. So if he starts 5 meters ahead, he's run his 95 meters in the same amount of time that Jill runs her 100 meters. So in order to get a fair race out of the two of them, you should actually start Jack 5 meters ahead of Jill. This example has a bird flying between 2 cars that are heading toward each other. So let me read the problem. We have 2 cars, 120 miles apart. They begin driving toward each other on a long, straight highway. One car travels at 20 miles per hour and the other at 40 miles per hour. At the same time, a canary, starting on one car, flies back and forth between the 2 cars as they approach each other. If the canary flies at 150 miles an hour and turns around instantly at each car, how far has it flown when the cars meet? So, if you don't think about the right thing, you could play with this problem all day long if you don't see the right thing to look at. So let me draw a picture here. Let's take a look at what's happened here. As they get closer, I'm just going to make little blocks of the cars. As they get closer, this bird is zipping back and forth between them, but the distance keeps getting shorter. So this bird, if we really were to look at its flight path, it probably would do something like this. Shorter, a little bit shorter, 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 shorter. And it keeps going all the way down to nothingness. So adding up all of those lengths is going to be horrible. And in fact, you would have to start doing rate times time and all that kind of stuff, and it would be kind of clumsy, I think. So instead, I'm going to concentrate on the cars themselves. How long until the cars meet? Well, what they're doing is in 1 hour, one car has gone 40 miles and the other car has gone 20 miles. So in 1 hour, they're 60 miles closer to each other. Now they have to go a total of 120 miles. In 1 hour, they went 60 miles closer to each other. That means after 1 hour, they are 60 miles away from each other. So they continue on. It looks like since they're using up 60 miles per hour, that this entire trip for the cars is going to take 2 hours. So we know that the cars will be driving for 2 hours. That means that the bird is flying for 2 hours. Now all I got to do is use one form of the distance equals rate times time, and I'll have the distance that this thing flew. The rate, we know that this bird is going 150 miles per hour, and he's doing it, he or she is doing it for 2 hours. Cancel out the hours, and you have 300 miles. Suppose you got 2 cups in front of you. One holds coffee and one holds milk. I am going to make the assumption for my problem that they're the same size cup, or that they're going to contain the same amount of liquid. Although I don't think it says that here. You take a teaspoon of milk from the milk cup and stir it into the coffee cup. Next, you take a teaspoon of the mixture in the coffee cup and put it back into the milk. So after this whole thing is done, the black coffee is just a little bit less black because of the teaspoon of milk. The milk is a little bit darker because you put this mixture back into it that was almost black. So what I propose is this. I'm going to draw a picture of 2 cups, just really, really crude pictures. And one of the measurements for coffee cups that I happen to be aware of is 6 ounces. And 6 ounces is a misnomer in this class. It's 6 fluid ounces. That's a difference. Ounces is weight, fluid ounces is volume. So this is also 6 fluid ounces. And what I'm going to do is I'm going to let this be the milk, and then this one over here will be the coffee. Okay, now each time they're transporting a teaspoon from one to the other. So instead of having the volume in fluid ounces, maybe I can get it in teaspoons. So I'm going to go to Google and see what happens. Let me go at this. So I'm going to say 6 fluid ounces, 2 teaspoons. Oh, nothing came. Oh, here we are. How much is 6 teaspoons? Tablespoons doesn't help me. What am I going to do? Oh, here we are. Okay, we have 1 fluid ounce is equal to 6 teaspoons. So let me go back to my thing. 1 fluid ounce is equal to 6 teaspoons. So 1 fluid ounce equals 1 teaspoon. And when I write these like TSP, that's the official designation for teaspoon. I need 6 ounces, so if I multiply both sides by 6, I'll have 6 fluid ounces will equal, that was wrong, wasn't it? 6 times 6 is 36 teaspoons. So let me redraw these cups in teaspoons because that'll be easier to work with. So we have 36 TSP milk. And over here, $36 TSP, and that'll be coffee. Now let me read the rest of this problem. It says, after you do this, they would like to know, these are very weird the way they're worded. They have three possible options here for an answer. More coffee in the milk cup than milk in the coffee cup, less coffee in the milk cup than milk in the coffee cup, or equal amounts of coffee in the milk cup and milk in the coffee cup. So I think the easiest way to do this is a way that is completely different from the way your textbook does it. Although I think their method is okay. I don't like it a lot, but go ahead and read it for yourself. So let's take a look at the first step. The first thing we're going to do is take a teaspoon of milk and put it in the coffee cup. So with that said, we're going to have 35 teaspoons of milk there now. And this is going to have 36 teaspoons of coffee and 1 teaspoon of milk. So what I'm going to do is look at the percentage of coffee that is in that cup. So the concentration of coffee, we have 36 teaspoons of coffee out of 37 teaspoons. So I can take this and multiply it by 100%, and this tells me what the percentage of coffee is. So let me pull up my calculator. So I'll do 36 divided by 37 equals, I'm going to multiply that by 100. So I get 97.297. Oh, 297 repeats. So 97.297, and that goes on and on. Okay, so we have 97.297 repeats, and that's the percentage of coffee. I'm going to subtract that from 100% to get the amount of milk in there. So let's go and do that. So I'm going to take, let me go minus 100 equals, ignore the negative. Here we have 2.702 repeating percent milk. So those are the numbers. That's not going to change because now you're going to take a teaspoon of this stuff and bring it over to the milk. So the last step will look like this. You're going to have 36 teaspoons of milk. Make a mistake there. 35 teaspoons of milk. And 1 teaspoon of this new mixture. So I'm going to say 1 teaspoon of 2.702% milk. So how many teaspoons do you have? What in the world did I put first? Well, what do we have all together here? We have 36 teaspoons of milk plus 0.0270, I'll round it to this, 3 teaspoons of milk. That's because of the concentration. I'm reading it right from here. This is 0.02702. I've just rounded it off there. Now, there are still 36 teaspoons in the whole thing. So let me go and do these calculations on my calculator. We have 35 plus 0.02703. So let me equal that. And I'm going to divide that by 36. And then I'm going to multiply it by 100, just like I did before. And I'm going to do the same thing roughly, 97.2973. So that's the percentage of milk. And then I'm going to do the percentage of coffee in there as I'm going to subtract this from 100. So I'll do minus 100. 2.70, how many am I doing? 2.703? So let's take a look at this. Well, if I were to round this to 4 decimal places, I would get this. Look at that. There's the amount of milk in the coffee, and there's the percentage of coffee in the milk. They look the same. Your book does a totally different thing than this, but I like using the percentages here to get a good handle on it. In this problem, we have Juan is decorating for a party in a room that has 10 large cylindrical posts. The posts are 8 feet high and have a circumference of 6 feet. His plan is to wrap 8 turns of ribbons around each post, from bottom to top as shown on the left in figure 2.2c.5. How much ribbon does Juan need? So let me go ahead and paste that picture. I'll try to make this as big as I can while it's still having it. Here, I'll put it over here. Maybe I can. So here's a representation here. What you see, if using this, I'm going to count 1, 2, 3, 4, 5, 6, 7, 8. So he's going to have 8 of these things. And you know, these are wrapping around. So the trick that they use, and they do this in other math classes as well, is they're going to cut it vertically and then they're going to lay it out flat. So what you have then is it was already 8 foot tall and 6 feet wide because the circumference of the column is 6 feet. That means that distance all the way around is 6. Now notice these lines are flat, but they'll be curved when they go on the curved cylinder. So what we need to do, what he can do then, is he can get the amount that he needs by adding up these 8 stretches of ribbon. So what we need to do, if I can find the length of one of these ribbons, it's going to be easy. So let me draw a picture here. I'm going to take and draw a picture of the very bottom one, if you don't mind. Something like this. So it's 1, I'm doing this part right here. That's the triangle I'm focusing on. It's 1 by 6, and we need to know that unknown length. The C that I put there is called the hypotenuse. The reason I'm using C is because we're going to make use of a very famous theorem. We're going to make use of a very famous theorem. This is called the Pythagorean theorem. And I can't possibly imagine a more important theorem, Pythagorean, than this one, because everybody seems to know it. It's been around for millennia. And so we can use it in this problem. The reason why I chose C for the unknown side was so it would match up with this triangle that I just showed you. According to this theorem, then I can take this C squared, and that's going to equal 6 squared plus 1 squared. 6 squared is 36. 1 squared is, of course, 1. I get C squared is equal to 37. To get C, then, use the square root button on your calculator. So it's going to equal the square root of 37. I'll show you what it looks like. On the calculator on the computer, it's this guy right here. Now yours will have a couple of them. You'll see one with a 3 out there, and you'll see one without anything out there. The one without anything out there is what you want. So you can test to see if you're pressing the right button by getting the same thing that I do. The square root of 37 is this number, 6.08276, etc. Now I'm going to round this to 2 decimal places because when you buy these lengths of ribbon, it's almost certain they're going to come in whole lengths of feet and not partial feet. So rounding is not going to be a big deal here. So I'm going to say 6.08 feet. And remember, this is just an approximation. But now, on this one pole, he had 8 of them. So for that one pole requires So we're going to have 8 times 6.08. And that's going to be 48.64. On the other hand, now he needs 10 poles. So he's going to take 10 times 48.64 feet. And I was a little bit sloppy here, so there, take care of that. And I'll just move the decimal over. And so he'll need 486 roughly feet of this ribbon. My guess is he's probably just going to buy 500 feet of it and just use the other amount that's left over for something else. Most people do like to buy extra just in case something goes wrong. All right, consider some railroad tracks on a hot day. What's happening here is we have 2 points on the railroad track a mile away, and the heat has caused the metal in the rails to expand. Seeing as they have no other way to go other than up, it looks like it will bow it along the middle here like this. Something like this will happen to it. So it'll be attached at these ends with railroad ties, but this part will be free because they only do ties every mile, I think. Yeah, so they're a mile apart. So it's expanded by 1 foot. So this is why we put 1 mile plus 1 foot. The railroad tracks, this length, if you measured it out, would be 1 mile and 1 foot because that happened because of the heat. The metal expanded and caused this to happen. So that's why we have 1 mile plus 1 foot. Well, what we want to know is how high this is. So I would like to know how high it is from here to the ground. So we want this letter H. Now, there's not a lot we can do here. We can estimate it in the following format. What I can do is, it did not what I wanted. Let me put the anchor point over here. I'll try to get my triangle like that. Not a good looking triangle, but there's another C. That's a hypotenuse kind of a thing. And then since it's right in the middle, this is 1/2. And so let me translate this triangle down here so we can see everything better. I'll put a little right angle thing down there. So we have its height. We have 1/2 of a mile here. Now up here though, 1 mile plus 1 foot, if I'm cutting it in half, this length will be 1/2 of a mile plus 1/2 foot. So I'm just going to, as my approximation, I'm going to say this is 1/2 of a mile plus 1/2 of a foot. Now, working in different units is not a good idea. I would like to have everything either be in miles or everything be in feet. I'm going to choose feet because converting 1/2 foot to a mile is going to be some ridiculous decimal that I would prefer not to deal with. So instead, let's get these distances. First, let's get the length of a mile. You can go on Google and find this, but I happen to know it off the top of my head. 1 mile equals 5,280 feet. Then if I want 1/2 of a mile, I'll divide that by 2. That's 2,640 feet. So let me redraw my triangle with everything in terms of feet. I still don't know that. That's what I'm trying to figure out. The bottom is 2,640 feet. And the top is the same distance except for 0.5 of a foot more. So we have 2,640.5 feet. And you may have guessed this, we are going to use the Pythagorean theorem. Anytime you have this, it should be automatic to you. The only thing is now, the hypotenuse part is up here. We know that number. So I'm going to put it 2,640.5 squared equals h squared plus 2,640 squared. And so then if I want to get h squared by itself, this is the calculations I'll do. 2640.5 squared minus 2640 squared. When all is said and done, I'll take the square root of it to get the value of h. So let's go ahead and use the calculator to get these numbers. So I'm going to take 2640.5 and I'm going to square it. Where's the square? There it is, right there. Now I'm going to subtract this thing squared from it. So I'm going to go minus 2640 and I'm going to square that. And then when you hit equals, it'll do the minusing. So I have 2640.25. That's h squared. To get h, I'll take the square root of that. I'll put the feet back when I get this also. Let me use the calculator one final time to just take the square root of that thing. And I'm going to really, since I'm just reporting the answer and it doesn't matter for anything, I'm just going to go one decimal place. I'm getting 51.4. And were these feet? Yes, these were feet. So that's quite a bit. I doubt this actually ever happens, but that was the nature of the problem there. Their method of solution is essentially mine, so they're not going to give you any more insight by looking at their solution than mine. China has always had a population issue. They've always tried to control it in various ways. And because they were once a farming society, I know they still are, but they were heavily farming, male children were more valued than female children. So they would like to have male children more than they would female children for strictly work. And so China instituted or thought about instituting a policy where you could only have one male child. And when you have the one male child, you're allowed to have no more children. So they were doing this in hopes of controlling the population. But there was another fear that if, suppose we just allowed one child, forget about the first male being born or one male, China did have a policy of just one child at one time. So what happened was, and the practice of desiring males is still holding sway in China to this day. So when people would only be allowed to have one child, if some of them had a female child, or knew it was a female child, they would abort it. And they would keep aborting until a male child appeared in their belly. Well, what happened in these cases is that a bunch of males were being born solely to one household, so one male child per household, and no other children. Well, what happened over time is that the females and male balance in China was way off. There were way more males than females, and now you have a bunch of men that can't find why. Well, men outnumber women by a large amount because of this. So there's issues with that, obviously. So a secondary idea is this, where we do it while you're allowed to have children until you have your first boy, then you have to stop. So let's take a look what happens here. Let's take a look at, on the first shot, on first pregnancy, you're going to have one of two things. You're going to have roughly 50-50 boys and girls. So you're going to have 50-50 boys and girls on the first round, 50-50. 50% boys, 50% girls. So this is first baby. They are done now. This column is finished because they've had their boys. Now these girls, though, they're allowed to keep going on. So the next round, second baby, still has a 50-50 chance of being a girl or boy. So you've got this 50%. Half of that makes 25% girls and 25% boys. Well, this keeps going like this. And the third baby, half of these people are going to have girls and the other half are going to have boys. So now you're at 12.5% girls. Look at what happens here, though. and we keep going, like 6.25, 3.125, etc. If you add all of these up, this actually goes on forever as an infinite sequence of numbers. You'll find that it's becoming around 1 as time goes on. And so this here, the 75% that are boys in this piece here, you add to these, and guess what? They're going to add up to the same amount, because you're going to have 25% boys were born into that group, 12.5% boys were born in that group, and it's going to add up to 1. So it does look like this new policy is going to maintain a balance, whereas the one before did not.